Hi everybody and welcome to chapter 40. Basically, chapter 40 deals with the wave equation. Basically, now we are really getting into the business of quantum mechanics. And first of all, basically, we're going to derive the wave equation. So let me have a check mark in here on the things that we really need to do. So we're going to derive the wave equation, namely Schrodinger's equation. Okay. Basically, we're going to start with the free particle like an electron or proton, it doesn't matter what it is, that is not under the influence of any external forces whatsoever. It means basically that it is not in a potential. After we do that, we're going to come up with basically with the wave equation. So we really have to have an explanation for that wave. So what does it mean? Okay, that wave basically. Okay, because you will notice that immediately is going to be a complex number, and of course when we do stuff in physics we never really can measure what a complex number look like, so we have to really explain what is that supposed to mean. Okay, and then we're going to go into generalize this idea of the free particle when it is actually inside a potential, when it is actually in interaction with other particles, so inside a potential, okay, in general. And then after that we're going to take the wave equation, basically, namely Schrodinger's equation, and separate it into two states, basically two parts, I'm sorry. Part that is depends on time and a part that depends on space. So we're going to separate the wave equation. What we are going to end up with is something called the stationary states. Basically, that a normal state for an electron, for example, will be a superposition of different stationary states, and that is basically the concept that is going to emerge from this one, stationary states. Okay, and the last point that I want to of course, we're going to go back into a particle. Of course, if we treat the free particle, it's going to have a problem. Okay, so we're going to really have a real problem, or at least an ideal problem. And the first one that we're going to be dealing with is a particle inside an infinite well. Okay, we're going to solve that equation there. Okay. And then after we do that, we're going to consider actually a finite well. So in this case, we're going to take the exact solution that we're going to find for an infinite well, and we find basically the behavior of how that is going to look like for a finite well. And we're going to come up with a concept from this one called the tunneling. So a particle that cannot basically escape a region can always find a way of getting to the other side, basically, and that is behavior unique to quantum particles, so quantum mechanics only. It's not possible, for example, for a classical particle to do that, classical object to do that. And we're going to close this one by not exactly solving the simple harmonic oscillator, but we're going to find basically the quantization of the energy for that case, simple harmonic oscillator, and the similarities between it and the classical basically treatment of the harmonic oscillator. There is a big distinction between this and the other one. So before I get into that point exactly, if you look at the harmonic oscillator, basically what you have spring attached to a mass in here, and you disturb the spring out of its equilibrium position, which was in here, and you let go of it. So it's going to oscillate back and forth between a maximum position and a minimum position. And what you notice there is that the particle spends most of its time in the extrema, basically either on this side or that side, because on one side it's slowing down to reach this point and then accelerating to leave it, but by the time it reaches back the equilibrium position, it's going to go super fast because the velocity here is at its max, the kinetic energy is maximum, the potential in here is its minimum. So classical particles have this peculiarity in a sense that this is where they spend most of their time, is in the location x naught or negative x naught away from the equilibrium. Quantum particles, though, they do the other way around. They spend most of their times in the middle, then in the extremities. So that is something that it's kind of interesting, and it's a difference between tiny particles and big particles. Anyway, so we have a big task in here. So let's first of all derive a wave equation. So up to this point, we were really kind of having issues in here after chapter 39 in the sense that particles seem to exhibit not just light wave behavior. As a matter of fact, light also, which is supposed to be wave, also exhibit particle behavior. So there was a component to particles due to Mr. de Broglie idea that if you have a momentum, you have actually wavelength. Namely, this leads to lambda equals to h over p. P is particle, is expected for electrons. So this is expected for a particle. Okay? Whereas this is kind of surprise. We're kind of shocked to see that a particle like an electron has a wave behavior. In the same token, for example, for a photon, which has a wavelength lambda, and again, that based on the arguments that Mr. Planck came up with, we were led to believe now that if you have momentum, you also have, I mean, that is actually the idea in there, but if you have wavelength now, it seems like you have momentum, so h over lambda. So this is expected for light, for example. This is no surprise. This is for photons, it's expected. This is where the surprise is. So this duality between particle and wave, namely wavelength and momentum, was kind of the dawn of a new physics. As a matter of fact, if you have frequency for a photon, you have energy. So if you have a frequency, the energy in this case, or you can express it in terms of, it's hf, or you can express it in terms of the angular velocity, basically by dividing by 2 pi, multiplying by 2 pi. 2 pi f is omega, and dividing by 2 pi, I'm going to write this symbol in here for h, and this is the symbol that we're going to keep on using. Namely, h is h over 2 pi, and of course f and omega are related to one another through this expression. So from this point on, we're going to be using the symbol h bar, which is just 6.626 divided by 2 pi, of course, times 10 to the power negative 34. So again, so this is where we are at that point, okay? So this is the whole, basically, summary of chapters 38 and 39. So one of them is 38, was actually dealing with this idea from this book. Chapter 39 dealt with this point in here, namely waves behaving like particles, and here particles behaving like waves. So, and the commonality in here is that this is based on the work. This is basically how Mr. Einstein was able to explain the photoelectric effect, and also now we use that for the Compton effect, and we use it for so many other things also that involve particles and waves. Okay, so the point being in here, now we are in a situation, and the situation is how can we find an equation that describes the behavior of particles in such a way that they have this wavelength in them. So we really have to come up with an expression that have a lambda in it. Okay, so an equation. Of course, F equals to ma is not going to work in this case because particles have momentum. They have F, which is dp over dt, and that's going to give us only a particle behavior. It will never going to give us this one. So this really marked the end of classical mechanics. This was the doomsday, if you wish, for Newton. So that second law of F equals to ma is no good anymore. Okay, it's not going to help us find any wave in here whatsoever behavior for this particle. So we need something else. So here is the idea behind it. This is basically how the reasoning that Mr. Schrodinger came up with. Here is the following. So basically we know the energy of a free particle can only be kinetic energy. There is no potential energy because it's free. Okay? So in this case it's just p squared over 2m. I mean, I know you're saying it's 1/2 of mv squared, but if you multiply here by m and you divide by m, you find that this is the momentum p squared divided by 2m. Again, since all of this expression involved the momentum p, that is basically how we're going to write this one. So the momentum for the particle is p squared over 2m. P is related to lambda via that expression. P, the momentum, is equal to actually h over lambda. Remember that lambda and the wave number k are related to one another via this expression. So I'm going to write this one again as h over 2 pi times k. K comes upstairs. And then again, I have that h over 2 pi, and h over 2 pi is h bar. So the momentum p now, if I were ever going to work with this equation, need to be written, or can be written actually, as h bar k. So this is the same thing as this one. So I didn't do anything except express it in terms of lambda using the wavelength. Instead of using the wavelength lambda, I'm using the wave number k. Okay? So we're going to write the expression for the energy now. as p squared, which is this guy squared, divided by 2m. So this is the energy. On the other hand, the energy, actually, we wrote it in terms of the frequency, or the angular frequency, as h bar omega. Okay? So this is basically the relationship of how omega depends on k. This is how the waves basically distinguish one another. We used it in the past for the wave equation, and we called it similar to it as the wave equation, as the dispersion law. This is omega, if you wish, as a function of k. Let me remind you, when we did waves, doesn't matter which chapter you pick up, it doesn't matter which chapter 32 from physics 2, whether it's chapter, what is it, 16 when we did, or 15 and then 16 also when we did also the waves, the mechanical waves. So basically all of this suggests that omega actually equal to kv, linear in k, I'm sorry. So this one is not linear. Clearly omega is proportional to k squared, so this is a different thing. And the wave equations then, if you guys remember, were of this form. The time derivative with respect to, I'm using the symbol psi in here because I'm leading to it, okay? So psi is any wave. Whether the electric field, whether the magnetic field, whether the displacement of a string on a transverse motion, basically, on a string, or whether actually the pressure or the density or the displacement of the air molecules for the case of sound, that is actually the same thing, pressure or S, or however you want to express it, or whatever you want to express in terms of the variables for sound. So that equation was always coming with this expression that it is equal to v squared, okay, times derivative of psi with respect to x squared. I mean, if you guys probably don't remember it in this form, you remember it with the other one written as the second derivative with respect to x of something in here. It doesn't matter. I'm just writing it psi for right now because I want to use the symbol psi, and that is a common word common symbol used for wave mechanics in here to distinguish it from all of these symbols in here. Okay, and minus 1 over v squared times the derivative of y with respect to t in this case is equal to 0. Obviously, this is exactly the same thing as that equation if I exchange now the variable y with this. Obviously, y here is a function of x and t. So I'm taking the one-dimensional problem, by the way, okay? Otherwise, this derivative will involve the partial derivative with respect to z and the partial derivative with respect to x and all of that thing. Anyway, so this psi, again, must be also a function of x and t, okay? So this particle also has this behavior, which is in x and t. Again, this is a normal wave, okay? This is the wave. Because if you guys remember, as a wave solution, we could take any solution we like, okay? If we use complex numbers, this is basically, or let's take trig functions, okay? Psi could be a combination, for example, of a cosine of a kx minus omega t, where k is going to be the wave number and omega is the angular velocity, plus another constant, which I'm going to call b in here, times the sine. This is a most general harmonic solution that you can think of. That depends, of course, on the initial conditions and the boundary conditions of the problem. So this is basically a wave, okay? Case in point, if I take the derivative with respect to x, yes, all I'm going to do is here I'm going to put a k in here and change the sign. So this is going to be a minus a times k times a sine of kx minus omega t. And in here the same thing, I'm going to put a k, but the sign stays the same and the sign becomes a cosine. So it's going to be bk times a cosine of kx minus omega t. So this is basically the wave equation when I take its first derivative. Of course, I did the second derivative in here. I don't need the first derivative. So the second derivative in here means that taking the derivative of the derivative with respect to x, of course, treating t as constant in this case. Again, I'm going to put another k in here, and the sign stays the same. So minus a times k squared. Of course, this sine function becomes a cosine of kx minus omega t. There are too many signs in here. One of them is symbol and the other one is the trig function. Hopefully you guys are not tripped in here. And here, when I take the derivative, I'm going to put another k in here, and the sign flips from a positive to a negative, and this sine function becomes cosine function becomes another sign again. So it's going to be minus k squared times b times the sine of kx minus omega t. If I pull out of this expression k squared with a negative sign in it, I'm going to be left with an a cosine of kx minus omega t plus b times the sine of kx minus omega t, which is exactly my function psi, the one in brackets. So that is minus k squared psi. Okay, so this is the second derivative with respect to x. I'm sorry. If I take the same thing with respect to t, I'm going to do the same steps, except I have a minus in here I have to be mindful of, because this wave I took, it was traveling to the right. Okay, there is another solution traveling to the left. So, but that's another one. Okay, so we're taking the one that is traveling to the right, traveling to the positive x directions. So again, if you take the derivative of psi with respect to t, I'm going to pull I'm going to pull a minus omega, and the cosine changes sine to a minus. So a minus times minus is going to be a plus. So that's the only thing I have to be careful with in here when I'm doing the time derivative. So I'm going to have a positive, let's write it in here to be explicit, omega times a, and of course the cosine becomes a sine function. So this is going to be a sine of kx minus omega t. And now what happened in the second term? Again, I'm going to put a minus omega, and the sine becomes just a cosine function. So in here the sine stays by itself. So I have a minus omega times b times a cosine of kx minus omega t. Okay, if I take this derivative one more time, I'm going to pull up another minus omega in here. The sine becomes a cosine, so the plus becomes a negative, and I have an omega already, times omega, that's going to be omega squared. If I take the derivative in here with respect to t, I will pull another minus omega, which is times minus omega becomes a positive omega squared. However, the cosine becomes a minus, so I have three minuses at the end. I will be left with another minus. So I'm going to be having in here minus omega squared times again a, the sine becomes a cosine of kx minus omega t, minus, again I already have a minus, so I'm going to put another minus, and the cosine will have its own minus when I take its derivative. So I have three minuses, so the whole thing will stay with a minus omega squared b times the sine of kx minus omega t. Okay. If we take the minus omega squared from this expression, again I have a cosine of kx minus omega t plus b times the sine of kx minus omega t, and we are in business. Okay, so this is in a nutshell basically the same thing. This is actually psi 2. If you look at the expression above in here, that was how we defined psi. A cos plus b sin, that is exactly the psi. But this is actually the first derivative or the second derivative? This is the second derivative, so I'm not careful in here in my writing. So this is the second derivative with respect to time. That was the first derivative. The second derivative now will do this thing. So the second derivative now looks like 2 minus omega squared psi. So if I write this solution, if I'm expecting this differential equation, which is that of a wave, to really describe harmonic waves this way, for a wave traveling to the right, for a wave traveling to the left, is going to be identical. Okay, so I plug in the second derivative with respect to time, which is this quantity, so it's going to be minus omega squared psi is equal to v squared times the second derivative with respect to x, which is minus k squared psi. So again, it's going to be minus v squared. V squared is part of the definition, basically, or part of the derivation that we get into this equation for waves. And then I have, again, the second derivative with respect to x has a k squared psi. Okay. Times, oh, sorry, there is nothing in here. I already did that. I already have the v squared in front. So Obviously, omega is positive, k is going to be taken positive, that wave number and the angular velocity. So psi, oh, I'm sorry, forgot the psi. You're right. I'm sorry. So I have the psi in here that I forgot. So psi is going to be cancelled in here because we want this equation to be true all the time, everywhere. So if you find it to be true at some point, or at some time, it doesn't mean much, so you really have to have it true. So you have to cancel with respect to x and t. So psi should not matter. And at the end, we have the dispersion law that I was talking about in the beginning, omega equal to kv. This is true for waves. So waves, this wave equation will give me omega equal to kv, but it's not going to give me what I really want, which is this expression in here, which is namely h bar omega. I'm going to leave the h bar in there, okay, if you guys don't mind. So it's not going to give me h bar omega equal to h bar squared k squared divided by 2m with the proper, yeah, it's not going to give me that, okay? So omega is proportional clearly to k in here, and in here it's proportional to k squared. So this differential equation is no good, so it's not going to help us, okay? So we need another one. And the other one is clearly coming in here. If I take the second derivative, obviously I have a minus k squared. And the first derivative will give me an omega. So this is a combination of the first derivative and the second derivative, with the first derivative with respect to time and the second derivative with respect to space. So this is what I'm going to do. Since I need an h bar in here, I'm going to take this equation and multiply it by h bar. Okay? I'm going to take this equation. Now I'll have h bar omega times this stuff, okay? I'm going to take this expression now, multiply it by h bar k squared over 2m and equate the two, basically, okay? So I'm going to take this equation, h bar squared k squared. I mean, I already have the k squared in there, so I don't need to multiply by it, divided by 2m. So if I do that, then I'm in business. However, there is a problem. You will see it clearly. Okay, I have h bar omega a times sine, and then I have here h bar k squared over 2m with a negative sign times a. So it's clear, but it's cosine function, and this is a sine function. So we need something to account for the phase shift, because the sine all of a sudden became a cosine. So we need another parameter in here, which I'm going to call c. So c is to fix the shift, because a cosine need to be matched with a sine, or a cosine need to be matched with a sine. And in the same thing in here, I have the second derivative involve a sine in here, and the first derivative involve a cosine in here. So maybe and hopefully that c that is going to fix this cosine and sine, basically shifts the cosine by 90 degrees enough to match both of them. So that is basically what this thing, it's a fudge factor, really. It's a factor to fix things so that the equation makes sense. So here is the equation that I really want, okay? I want an h bar times the partial derivative with respect to t be the same thing as h bar squared over 2m times the second derivative of psi with respect to x plus the fudge factor in here, something to fix things around so that this thing works for me. So let's do that. If I multiply this, obviously I will have the h bar omega in here. So let's write that. And then I have an h bar omega in here too. So I'm going to take h bar omega as a common factor. So I will be left with, on one side, h bar omega as a common factor, open parentheses. So what I'm left with is this a sine minus b cosine. So it's going to be a sine of kx minus omega t minus b sine of kx minus omega t. Here is the expression I'm looking at. It's the first derivative of psi with respect to t multiplied by h bar. Took omega out because it's common for both terms. I'm going to have an a sine minus b cosine. I'm sorry, did I write b sine? That's not correct. It's actually b cosine. So you have to really be careful in here because it can lead to trouble. Okay, it's the second term in this expression, which is b cosine with a minus sign. Okay, I'm going to come to this expression multiplied by c times h bar over 2m, this term. I have already k squared out with a negative sign, so this must be equal to negative k squared times h bar squared, I forgot to multiply by that, divided by 2m, times open parentheses now. And the open parentheses, of course, has the same function that we started with, which is the a cos plus b sin. So a cos, times c, times the fudge factor that I was making a big fuss over. So a cos kx minus omega t plus b sin kx minus omega t. Okay. First of all, first thing first, we want the dispersion law in this case, or the version of it in here if it's called dispersion law, to be true. Namely, these two terms are equal. Namely, we want h bar omega equal to the same thing as h bar squared k squared over 2m. So we want that. That is by choice. That's the whole purpose of this, so that the wave behavior is described for this free particle. So this term and this term cancel. So what we're left with is the following then. That a sine of kx minus omega t minus b cosine of kx minus omega t, which is the stuff that is left in between the parentheses in here, must be the same thing as, okay, I have a minus in here times a, so it's minus a times c, so it's going to be minus ac times cosine of kx minus omega t, and then here I have a plus b times a minus again, so it's going to be minus bc times the sine of kx minus omega t. Okay, it's really, now we're trying to find an equation for the free particle so that this stuff works. Okay, that is basically what we're trying to do in here. Obviously, this sign, because we want this to be true all the time everywhere, must be true all the time everywhere, which means that this sine function in here must match with this sine function. So this term and this term must be the same. Their coefficients must be the same. The coefficients of this function and this function must be the same all the time too. So we're looking for an identity, really. We're looking for an identity. For that to work, a must be equal to negative bc. A must be equal to negative bc. Okay? And then also negative b must be equal to negative ac, or b is equal to ac actually. So b is equal to ac. If these two equations are true, then we have an identity. This coefficient of cosine matches with this coefficient of the cosine, and this coefficient of the sine must match this coefficient of the sine. Obviously, a and b are arbitrary. It doesn't matter how much you take them. They depend on the initial conditions, boundaries conditions, or whatever. So this c factor needs to be chosen so that this works. Okay, so how can we do that? Obviously, sub this value in here, and you're in business. That means a is equal to minus b, which is ac, times c, which is c squared. A cancels from here because it's arbitrary, we don't care for it. So that means c squared is equal to negative 1, which means that c is equal to negative 1, that is. C is equal to I, basically. Okay? As a matter of fact, it's either plus or minus I. Okay? Because the square root of negative 1 is either I or negative I. And the equation that I am looking at for is the following. So it's really going to be h bar times the derivative of psi with respect to t, and that is equal to basically I times h bar over 2m times the other one. So the coefficient really that we need, and the I would work better than the negative I because the other one will not make sense, and you will see shortly why. Okay? So let's write the equation in here correctly. So this is the equation that we wrote for us to work with, so that we imposed on it this condition, okay, for a free particle, obviously. So we're going to write this one and change now the C to what we found to be I. So if I do that, the equation then becomes h bar, the time derivative of psi with respect to t, is sum I times the h bar squared over 2m times the partial derivative of psi with respect to x. Okay, the second one. This is typically written as follows, and I will show you how it's written. So we multiply by I everywhere. So this I will become in here IH bar times d psi over dt, and we note that I squared is equal to -1, so that is going to be equal to negative h bar squared over 2m times the partial derivative of psi with respect to x. Okay. The reason why we write it this way instead is because this quantity is actually associated with the energy. Okay. Because if this function has in it an exponential of writing stuff in complex, because the solution now psi is complex, okay, that is something that we did not really anticipate to begin with, but that led by itself, so it's not a choice in here. Okay, so psi now must be a complex number, and instead of doing cosine sine, we're going to use the Euler expression for the cosine. So if you have a cosine alpha plus I sine of alpha, that is according to Euler expression, that is exponential of I alpha, and derivation for it is really straightforward from the Taylor series. Okay. Anyway, so now we're going to have this time dependency because it's a free particle. It's going to have this either cosine or sine, namely it's an exponential of I something. But if you notice that I've used exponential of negative I everywhere, negative omega everywhere, so this expression in here, I expect the energy to be of this form, exponential of negative I omega t. Okay, so if I take its derivative with respect to t, so this will drop for me in negative I omega times, of course, my h bar in here, which is an IH bar, and now all of a sudden negative I squared, which is positive, so this energy is really h bar omega, exactly how I wanted it to be. Okay, exactly how I want the energy to be to begin with. That is how we started with this whole thing, this whole argument in here. We wanted the energy to be h bar omega. So if we write it this way, we are in business. So that is why we are writing it in this format, IH bar, which means this expression in here, because if this were a complex number, you're going to drop another. So if this was an exponential of positive I, or it doesn't matter, or negative ikx, exponential of ikx, so if you take its derivative twice, it's going to drop the first time ik, the second time it's going to drop another ik, and I squared becomes the -1, which is really what cancels this one, and we're back in business. So that is actually the momentum squared divided by 2m, namely the kinetic energy of the free particle. So the negative now is required. So this expression looks like it's that of the energy of a particle expressed in this format. So now when the particle is not free anymore, non-free particle, so it's in some sort of potential. Okay, if the particle is in some sort of potential, so don't tell me we're talking about friction and non-conservative forces and all of that, because we're dealing with a particle in here, and at this point it's going to friction with what? Okay, so all of it is just potential energy in this case. Okay, so then in this case I expect the first side to tell me about the total energy of the particle. So this is not going to change. On the second side now, I have a psi function in here being acted upon by, first of all, the kinetic energy term. So minus h bar squared over 2m times the second derivative of psi with respect to x. This is the potential, this is the kinetic energy. Obviously, we're using classical mechanics because we're assuming this particles in here are non-relativistic, otherwise it's going to be a problem. This is the total energy now. Okay, so this is the mechanical energy. So all I need to do is to fix this one in here is by adding the potential energy, of course, multiplied by the function psi. You're asking, okay, you didn't derive anything, you just took an extension of something we know from classical mechanics. and you basically wrote it in terms of, yeah, you're right. Okay, so this is how Mr. Schrodinger basically proceeded from this one on, and based on that, you're going to find the results that are probably the most accurate results from this. So in other words, at this point, we're writing the equation assuming that it is basically some sort of a hypothesis, if you, I'm sorry, some sort of a principle, if you wish, or some sort of a law, okay, because it works. So this is the potential energy term, okay. So this is basically how we're going to be dealing with this equation. Obviously, this equation is complex, and we better have some sort of an explanation for what this psi means, okay. Mr. Niels Bohr came up with an explanation for it based on the following argument. He says the following: the function psi itself is a complex number, obviously, and its amplitude squared has a meaning. It really tells me about the distribution of probability distribution basically for this particle. Here is his reasoning why that is. When we looked at, for example, the photon itself, when we did physics 2, okay, what we said there is that we shine a light, it goes through, for example, a double slit or a single slit, it doesn't matter. When we go to the plate on the screen and collect the light, what we're collecting is we're collecting the intensity of the light. And the intensity of the light is actually proportional to the square of the electric field. If you guys don't remember that, it's 1/2 of epsilon naught times E squared, okay? Or that of the magnetic field, which is also the same thing. So this is actually the magnetic field, B squared, okay? And this, on average, is just the maximum value, actually. The intensity in this case is just the amplitude of this stuff, okay? So this is the amplitude of the wave. As a matter of fact, this is true also for waves on a string. Because if you calculate the energy on the string, you're going to find them that they are proportional to the amplitude in here square of the oscillations. So this distance in here, A squared. And this is actually true also for sound too. Sound intensity is proportional actually to the maximum displacement of the air molecules in this case. So this behavior is true everywhere for waves. So it should be also true in this case in here for this one too. So what he said in this case is the wave equation psi squared, if I calculate this quantity between x and plus delta x, okay, what I'm looking for in here is the probability of finding the particle in between actually x and plus x delta x, x and x plus delta x, or dx, okay. So this is basically his reasoning. So now psi squared itself is a probability distribution function, okay. So psi itself is probability distribution function, and psi itself is actually the amplitude of that function, or actually, so psi squared is the probability distribution function. If you're interested in finding how fast the particle is moving, you have to multiply this probability function by the parameters that define the velocity, and from there you're going to sum through all of the probabilities and divide by that, and you're going to find exactly how probable this particle will have that speed. So in other words, basically, this is what we're dealing with in this case. So it's really a probabilistic theory at this point. So psi squared is just like the intensity of light. So there is, if you shine it through, basically, if you shine light through double slit and you go with your screen, there is a probability of finding basically how much intensity here and there. You're going to graph that function, and there it's going to be maximum in some places, minimum in some places, and so on and so forth. Same thing with the electrons too. If you do the same experiment with them, what you're going to find in this case, their wave in this case, described by psi, this complex number psi, at the end is going to give you the probability distribution of finding the electron somewhere. So this is basically the interpretation that was due to Mr. Niels Bohr for this equation, for Mr. Schrodinger's equation. So this is Schrodinger's equation for 1D, of course. We're going to deal with the equation in 2D later on. Okay? And this is Niels Bohr interpretation. And this is the one that is we're going to be using in here. And actually, like I said in here, the whole thing in here is that how accurate this theory is, and it's amazingly accurate. Really, it's something that is unimaginably accurate. So that is really the whole beauty of this. So we're going to take it because we proved this part of it for the free particle, and we just took an extension of this one for a particle that is actually not free, that is inside a potential. Okay. Well, usually this equation is dealt with in this following way, because if you can clearly see is, I'm going to write it in its standard form. So this is capital psi divided by t, I mean the second derivative with respect to time is IH bar is equal to minus h bar squared divided by 2m. This part is due to the kinetic energy, okay, the whole part, not just this term, the whole thing, because that's going to put me just the k squared as I needed, plus now the potential of the particle in a field of some sort, psi again, and this is the full-fledged differential equation that we're going to be dealing with. Obviously, it's a partial differential equation. Solving it is not usually the easiest thing in the world. We're going to do some trick in here, if you wish. We're going to consider the following. We're going to consider if we can separate the function psi, capital psi, into a little psi. Obviously, this function depends on two variables, at least in 1D, x and t. Okay, so we're going to separate the time, the space behavior from the time behavior of this function. Okay, and see how is that going to work for us. See if we can find a solution for this equation in general in this case. Okay, so obviously if I take the second derivative of psi with respect to t, this psi has no business whatsoever. It all has to do with this derivative of t with respect to t, and that is a straight out derivative, so it's not a partial anymore because of the fact that this function t has all the time dependency in it, so it's going to be just a straight derivative. So the second derivative of psi with respect to t is simply going to be this psi, which is the spatial derivative times dt over dt, and this is basically how the behavior of this function look like. Now, if I am interested in the spatial derivative in this term in here, again that looks like this. The second derivative of psi with respect to x is going to be in the same fashion t sub t times the second derivative of psi with respect to x, because all the spatial behavior is described by, I'm sorry, did I write capital psi? I meant little psi in there, lowercase psi, okay, with respect to, I usually give it a tail in here when it's lowercase, okay, divided by dx squared, because all the spatial behavior is described by the lowercase psi. So if I take this equation now and sub the values in here, this is how the equation look like. So I have an IH bar times the second derivative with respect to time. So I'm going to pull a psi in here and leave that. So I have a psi in here. I know this depends on x, so I'm not going to write it now. Divided by dt squared is equal to minus h bar over 2m, h bar squared over 2m, times the second derivative of psi with respect to x. Again, I have a t in here, times the second derivative of psi with respect to x, plus u times t times psi. Okay, I'm going to take this equation and divide it by t times psi, divided by psi basically, t times psi. Okay, if I divide that, this psi and this psi cancel on this side, and this t and this t cancel, and this t and this t cancel, and it will have the left hand side look like this, IH bar squared. There is no IH bar squared, this is an H bar only. Okay, hope I did not write it somewhere else. Okay, good. So I will have an IH bar times the second derivative of t with respect to t. Why is the second derivative? Why the second derivative? It's only the first derivative that we need in here. Sorry about that nonsense. So we need just the first derivative in here with respect to t. You guys need to pay attention to what I'm doing in here. Hopefully fix this nonsense stuff in here, because the equation has just the first derivative in here, so all of this is wrong. Okay, what else did I write it wrong? I didn't write it wrong in here. Good. Okay, So again, we need just the first derivative in here with respect to time. Okay, so everything looks good now, hopefully. Okay, so we need just the first derivative in here divided by t must be equal to minus, again the t and the t cancel, the second half looks good, so it's going to be minus h bar squared over 2m times the second derivative of psi divided by dx squared plus u, and the whole thing in here is divided actually by psi. Okay, I need to, okay, this term is divided by psi, and this term is by itself because it has two psi, t psi, and the t psi will cancel for that term. Oh, sorry. You have to be very careful with these things because sometimes when your mind drifts a little, you're out of basically things. Okay, the potential in here depends on space. Okay, I forgot to mention that. That is basically potential. You have particles sitting still and the particle is free to move with them. So this potential cannot be time dependent, otherwise we have a problem. We have a non-conservative force in that case. So this side of this equation, remember t is a function of t and psi is a function of x. This side of the equation depends on t only, whereas this side of the equation has x in it only. And here the two variables are completely independent of one another. Time and space have no connection whatsoever in classical mechanics, and even in quantum mechanics. So in this case, even in relativity, what I'm saying, it's still independent variables. So in this case, on this side, which has only time in it, and this side that has space in it, and they must be equal, the only way for these two equations to be true, that they must be equal to a constant. That constant is clearly because I have the potential energy. This must be actually the total kinetic energy of the system. So I have the kinetic energy plus potential energy, so this side must also be the total energy. So motivated by that idea, I'm going to write that this side, I h bar, derivative of t with respect to t, must be equal to E, the total energy, which is also equal to minus h bar over 2m times the second derivative of psi with respect to x divided by psi plus u. This must be true. Okay, this equation must be true. So this is basically how the equations, now I have two equations instead. So the first one looks clearly like the derivative of t with respect to t is equal to minus, so when I move I to the other side, it's going to be a minus E over h bar, okay, times t. And the second equation looks like it says that basically minus h bar squared over 2m times the second derivative of psi with respect to x plus u times u's of x times psi is equal to u e times psi. Basically, I multiplied everywhere in the second equation by psi. That's why I picked up an e in here. Okay, so this, I forgot the I in here to write it. So there's an I in here. Okay, so the first equation is integrable. It's just the integral in this case. The second one, you have to solve it because you don't. This is the most general case. This is actually called the time-independent Schrodinger equation because there is no time in it, only space. So this is the time-independent Schrodinger equation. Okay, and this one we can solve it actually. We can find that by just moving the variables a little. So dt over t must be equal to, when I multiply in here, which is kind of physics thing we say, you have to go back to the finite values and multiply and then take the limits. Okay, back to this expression, it's almost the same thing. So minus I, what is my E over h bar dt, and once we integrate this expression, the side will give me ln, and this side will just give me an negative e over h bar, and when you integrate it, you're going to find the t sub t basically equal to an exponential minus e t over h bar. Okay, I did not write that constant because this whole thing is just multiplied by psi, lowercase psi, and that must satisfy the equation itself. Okay, so we're going to throw the conditions back into the big function psi. Okay, so ultimately once we found psi and once we find t, we are still dealing with this is the one that is supposed to be the whole equation, which is written as psi of x now times an exponential of minus ie t over h bar. Okay, so you're asking what happened to the constant it went in here. Okay, so that this whole thing now has a constant carrying with it. So this is basically what we mean now. This is basically the equation that we have to solve, and this becomes the so-called eigenvalue problem, because this equation will need to be satisfied, and you will see that it can only be satisfied if the energy is quantized, and then the solution, which is really this one, is going to be the superposition of those different quantized states. Okay, and each state of them becomes what is known as a stationary state. So if you actually go and do an actual measurement by finding, for example, the psi squared, you're going to find one if the particle in a given state, as if that superposition now collapses all of it on that special state with the measurement. So it seems like the measurement influences the result, because this is going to be a sum of all of the other eigenvalues in here. So this is basically a condition, the equation that we have to solve in this case. We're going to see practical examples of how that works. Okay, so again, for the case of the free particle, u is equal to 0 basically, and this equation becomes just the integral of this one and going to give me back the expression that I worked with, because this becomes like a harmonic oscillator basically, a classical harmonic oscillator. So it's going to be a cosine and a sine and everything else that we were doing with, except in that case we will have a problem if it's just a single solution. When we sum that psi squared dx, obviously the complex numbers will cancel, and it will just have the amplitude, which will give me an infinite probability when I sum it from negative infinity to positive infinity. That means that the particle is somewhere in space. Okay, and that's basically what that means. Now if I take two waves and combine them, then it becomes more and more localized, which means that really I have to take a bunch of these waves called the packet to really have the idea of basically localizing my particle in here, and this is the idea behind it. So in a nutshell, this is basically the equation that we are going to be dealing most of the time trying to solve, because the temporal behavior is carried by this expression in here, okay, for the energy. Once you find it, you're going to put E in here, and you're going to have the temporal behavior. Of course, don't forget that at the end, psi by itself does not mean much. You really have to have psi squared of x and t, and I must remind you that this is actually equal to psi of x and t times the complex conjugate of this psi of xt. And when I do the complex conjugate in here, I will change its sign, and at the end I will end up with basically just psi squared, the little one, because this is going to be actually equal to psi of x and t exponential of negative h bar et over h bar, okay, times psi star. So this is psi star, this is the complex conjugate. So where basically anytime you find an I, change it. So this one potentially can be complex, that's why I have to write it this way, exponential of a positive I e h bar over t over h bar t over h bar. Okay, so in other words, this is the complex conjugate of this number. So when I multiply them, absolutely I'm going to end up with exponential to 0, which is 1. So at the end, I'm going to end up back into the complex conjugate of this just the spatial parameters, which is just the absolute value, basically the modulus of this complex number squared. Okay, again, this is how stationary states behave. So this is called the stationary. So what is meant with a stationary doesn't mean that it is fixed in space, still has time dependency, but it means that the energy is well defined in that state. Okay, it's En that solves this equation. Okay, so this is the time independent Schrodinger equation, because it has no time in it, and it's just an ordinary differential equation, which is still not an easy equation to solve. So let's try to find that solution for our case. The first case we're going to consider is an infinite well. So here is an infinite well. Basically, you have a particle that is trapped in a region of space between 0 and L and cannot go anywhere. So the potential is equal to 0 when x is less than L but greater than 0, and the potential actually is an infinite. U of x is infinite when x is more than L or x less than L than 0. Okay, so that is basically what an infinite well is. Okay, so the particle cannot go out of this region. Basically, it's trapped in there. It cannot go anywhere else. Okay, so if that's the case, then Schrodinger's equation basically becomes, we're going to solve it just between this region where U is 0. Okay, so the particle cannot exist outside of that well. So the equation then becomes simply minus h bar squared over 2m times the second derivative of psi with respect to x is equal to E psi, because, and this is between x less than L, less than or equal to L, I should say, because you can touch that and cannot leave it, okay, and 0. So basically, that is where the particle can survive. Outside, you cannot write the equation in there because the particle cannot exist in there. So it exists only in this box. And U is 0 in this region of space, okay? The potential is exactly 0. So it's free to move as long as it's between 0 and L. Okay. So this equation now is similar to that of a harmonic oscillator, except the harmonic oscillator has a time derivative. This one actually is a spatial derivative. So again, I'm going to write this equation as psi of x as simply some complex number. We're going to call it a1 times ikx plus a2 exponential of negative ikx. And if you're wondering what is that k, it's exactly what it means, okay? K is related to, so that the energy E basically is equal to h bar squared k squared over 2m, okay? That is basically the whole thing in here that we've been dealing with. So in other words, you can define the momentum, and this is the wave number, and this is the expression that we have in there for the free particle, basically. But it's not free anymore. It cannot be free from negative infinity to positive infinity. It's free only between 0 and L. Okay? So we're going to impose a condition now that its wave equation must vanish at this point because the particle cannot exist outside. There is a probability of 0 being outside. So psi is equal to 0 here, and psi is equal to 0 here too, because it's no matter what, okay? So that is a condition that we're going to do. So the boundary condition in this case state that psi of 0 must be 0. That means that a1 plus a2 is equal to 0 because of the fact that a to the power 0 is 0 and a to the negative 0 is 0. So a to the negative 0 is 1 and a to the positive 0 is 1. So a1 plus a2 is equal to 0. That means that a2 must be equal to negative a1. Okay? So from the get-go, this function has this look to it. It looks like psi of x must be equal to a1 times an exponential of ikx minus exponential of minus ikx. Okay? Well, if you remember Euler's expression, exponential of ikx is simply cosine of kx plus I sine of kx, and the complex conjugate of that one is simply cosine of kx minus I sine of kx. So if I subtract the two quantities, this cancels, and I will have a 2i in here, and I minus I, it's 2i. So psi as a function of x then must be 2i a1 sine of kx. Okay? I'm going to carry this 2i a1 because the whole thing is actually a complex number, so I'm going to call it just c, the constant c. So psi of x is some constant times sine of kx. We're going to find what that constant need to be. Okay, sure, for sure. So we know also sine of L must be 0 too. Psi of L must be 0 too, because the particle cannot exist beyond the point x equal to L. So in this case, that means that sine of KL is 0, okay? Which means that KL is an integer multiple of pi, okay? sine of 0, sine of pi, sine of 2 pi, sine of 3 pi, sine of 5 pi, or sine of negative pi, or whatever numbers that you'd like to have in here. Obviously, we're going to pick up the number that makes sense for us, which is the positive numbers, because the wave number is positive, because we already included the negative behavior in the second term. So k is going to be positive, so n is going to be from 0 to whatever number you have. Actually, it cannot be 0 because that's a stationary particle, it's actually fixed particle, and that's going to be actually n equals to 1, and so on and so forth. So k must be equal to n pi over L, okay? Which means that the energy must be equal to n squared, pi squared over L squared, over L squared in this case, okay? The energy is also dependent on that index number, so it's n squared times h squared, h bar squared that is, divided by 2ml squared times pi squared, okay? You can write this expression a little differently if you like, by basically rearranging that term with, again, h bar and h and all of that if you like, and you're going to pick up a 4 in here divided by 8ml squared and write this one instead of. But the key thing in here is the energy is quantized now, and this solution that we came up with earlier for the time part of it is exponential of negative I, what is it, negative I E is going to be in En now, specific values, and those are the stationary values that we've been talking about. And that is basically the whole point of this. So the wave number now, k, which is related to, by the way, to 2 pi lambda, 2 pi over lambda, must be an integer multiple of pi over L, in which case in here that the wavelength itself, lambda, is equal to 2L over N. This is similar to actually standing waves on a string. It's identical, okay? So, and here I cannot have lambda equal to infinity because if n is equal to 0, that's why I have to restrict n equal to 1. That is the first mode, and so on and so forth. So n is the first mode. Second, in n, I will have 2 nodes. So this is the well. For n equals to 1, I basically have, this is a node, this is a node, and the middle in here is my NT node. So this is how the psi would look like in this case, okay? For n equals to 2 in this case, the wavelength is going to be, lambda is exactly equal to L. So this is L from 0 to L. So in this case, this whole thing is going to be a wavelength, because this is a half wavelength for n equals to 1. For n, this case, it's going to be this is the second stationary mode in this case. So this is n equals to 2. And so on and so forth. If you guys remember the discussion from, so for n equals to 3, in this case, so it's going to be 2L over 3, or 2/3 of the way is your wavelength. So this is your wavelength, plus a half wavelength. Again, this is n equals to 2, and so on and so forth. The energy levels, though, are completely different. The energy levels, they are spaced differently. So for n equals to 1, this is how this looks like. So again, I'm going to call this h bar squared, pi squared over 2ml squared as just an E naught, okay? So this is going to be just n squared, E naught squared, E naught, I'm sorry, where E naught, or E1 I should call it, because that's for n equals to 1. E1 is going to be h bar squared, pi squared over 2ml squared, okay? Plug in that number in there, then the first level is going to be E1. So this is n equals to 1, and the energy level is E1. The second energy level is 4 times as much, because remember, 2 times 2, 2 squared is going to be 4 times. So this is the second energy level, n equals to 2. So this is E2. The third level is actually 9 times as much, okay? So this is n equals to 3. And in this case, the third level is going to be 3 squared, which is E3, 3, which is going to be 9 times E1. This is 4 times E1, and that is so on and so forth. So the gap in here increases big time between the energy in here. Between this one and this one is actually, what is it, 3E1. Between this one and that one is 8 E1, the energy gap. And you can basically, the energy gap between the second and the first is going to be, the second and the third, I'm sorry, is going to be 9 minus 4, so it's 5E. K1. So we have a full quantized energy, which is perfect for every purpose that we're doing in here in this case. And this is the particle when it is inside an infinite well. What happens when it is actually in a finite well? Well, in that case, it's going to be different. Obviously, the actual state of the particle is a combination of all of them. I mean, the mathematical one. So there is a linear superposition of all of them. So you add them up, and you do what is known as Fourier basically expansion, and it's going to be the sum of all of them. If you do a measurement, actually, you're going to find that in one or the other one, or some specific state in here, either in the excited state, the third level, or the second one, or actually in the fundamental state, depending on what you do, how the particle is. And in that case, there is that so-called collapse of the wave function in here, and that's how we interpret it in the actual measurement. At any given point, at least before the measurement, the actual state is the linear combination of all of the states, these so-called stationary states. And these are the stationary states. Okay. What happens when the well is not really infinite, but rather it's finite? So in this case, it's equal to 0 everywhere except after, between 0 and L, it's V is equal to U is equal to 0. But in here, it's actually equal to U naught or V naught. Okay, we usually use the symbol V naught in this case. Okay, so this is basically how the wave function is going to behave. Okay, obviously the equation is going to be very hard to do. So for x less than 0 or x greater than L, the equation that we need to deal with is h squared over 2m times the second derivative of psi with respect to x plus v naught psi is equal to e times psi. Okay, if I move v naught to the other side, and since, or let's move the second derivative to the other side and keep v naught. So it's going to be v naught minus e, whatever energy it has, times psi is equal to h bar squared over 2m second derivative of psi with respect to space. Okay, I'm going to call the ratio 2m h bar times 2m divided by h bar. I'm sorry, 2m divided by h bar times this number v naught minus e as some sort of a, if it is positive in here, as some sort of a kappa. Okay, the particle, the potential is high enough, and the energy of the particle is low enough. So basically the equation that I'm dealing with in this case is of the form of second derivative of psi with kappa squared, okay, times the second derivative with respect to x is equal to kappa squared times the second derivative times psi itself. Okay, if kappa is positive, that's why I put it kappa squared in here, then the solution for this equation is of this form. Psi is going to be an exponential, actually. There is no complex numbers or anything like that with it, because if I derive this one of the exponential, so it's going to be an exponential of kx plus the exponential of negative k kappa x. Okay, and of course I'm going to need a constant in here, which I'm going to call, because I used the a's, so I'm going to use the b's now. Okay, this solution will be true for x less than 0. Because this one cannot be there, because the particle will go toward infinity, and we can't have that. So the particle can exist, but it's still mainly trapped actually in the well, although it's of a finite level. So in here it's going to decay exponentially, because for x negative this decays exponentially. This will be true though for x greater than L. So again, in this case, the particle again will exist, but as x grows bigger and bigger, this number decreases less and less until the particle basically is in there. So if I take any mode, it doesn't matter. Let's take the third mode in here. So this is what we expected when it was basically a stationary, when it was an infinite well. Okay, but now, since it's not an infinite well, we expect the decay exponential to this region, and it's going to go to 0. So it doesn't sharply become 0 in here, but rather it's going to decay exponentially to 0. So this is basically how this boundary conditions are met in here. Of course, we can continue the solution and find some stuff in here in between, and continuity and stuff like that. But that is the point in here. Let me look at the well when it is inverted, when it is basically backward. So here is the well when it is inverted. In other words, it's 0 everywhere except it's V naught somewhere between 0 and L. So it's basically in here, it's 0. So expect a wave behavior in here, and in here it's going to be, so this is 0, this is L, and we expect another wave behavior in here. But there is a potential in here, and if the particle doesn't have enough energy in it, that means V minus E is going to be positive. But because of what we just saw, the particle does not sharply stop in here, it's actually going to extend a little. The same thing, it's not going to sharply drop in there to 0, but it's going to extend and then drop to 0. As a matter of fact, if the well is not big enough, the particle can extend enough so that it can exist on the other side too. This is what we mean by tunneling. So although there is a solution on this side, and if the particle happened to be on this side, and there is a barrier in this case, so this is a barrier, potential barrier, so the particle can find, if this barrier is not wide enough and the intensity is not big enough, find itself on the other side and satisfy the other condition there. So the probability of finding it in here is not 0. This cannot happen with classical particles. Classical particles cannot, basically, you have to have a very high enough kinetic energy for it to basically go around the potential and go to the other side. But if it doesn't have enough kinetic energy in it, it's not going to basically make it to the other side. And this is true only for quantum particles. Okay. The final point of the discussion, as promised, is the point dealing with the harmonic oscillator. The reason why this is actually important is because if you look at the potential, any potential, is that basically it has some minimum somewhere, and then it's going to behave, basically it's going to have the rest of the behavior in there. We expect the particle to reside somewhere in this region when x is small. When, for example, imagine we're talking about, for example, an atom in a solid of some sort. If that atom can basically is bound in that potential, so it's not going to move. But as you heat up the material, it starts to vibrate back and forth, or the electron starts to move back and forth. As long as it's trapped to its atom, it's not going to move further, very far away. Okay, you really need to have a lot of agitation in it to excite it from its state. So this is basically what we're dealing with in here. In this region, the potential can be approximated to 1/2 of kx squared, where k is a property of that basically returning the object back. So it's really the restoring force for this case. Okay, just like the spring, the mass in the spring system. So the model for the mass spring system is really a model that approximates a lot of the problems in physics, and this is one of them, okay, for particles. So now here is the equation that we're going to be solving, we're going to be dealing with. The equation, again, the time-independent Schrodinger equation, is negative the second derivative of psi with respect to x plus this term now, 1/2 of kx squared, psi is equal to e, psi. This equation is very hard to solve, okay? Very, very hard to solve in general. So what you do in this equation, you move the e to the other side and start working with it. So you say minus h bar squared over 2m times second derivative of psi with respect to x squared plus, or let's put the plus in there and move the sign in there, okay? So we're going to put the plus sign in here. So it's plus, when I move the e, so it's going to be an e in this case, minus 1/2 of kx squared. Psi is equal to 0, okay? You can convince yourself that this is not wrong. Here is the trouble. If the particle has ventured so far away from the equilibrium position, okay, further than even where it's supposed to be because of the tunneling, so it could exist potentially outside of x0 and negative x0, okay? So this is, in classical mechanics, the harmonic oscillator can oscillate between these two extrema, okay? If the particle is in here, okay, we don't expect it to, even in quantum mechanics, to last that long. So we really expect that psi function to decay rapidly with x. So it has a lot of basically, the position is far away from it. So what we're going to say in here, we're going to ignore e for that case, okay? So basically what we really need to solve is this equation then, far away. So we can't really say that psi is equal to 0 here, but we expect it to decay to 0. That is the point in here. But we want to know how that decay happens to be, okay? for large x. Okay, so this is the equation that technically we're supposed to be solving then in this case. Minus 1/2 of k times x squared, the second derivative, is equal to 0 for those places. Okay, we want to see how the decay is happening. This is still a very hard equation to solve. So what we say in this case is there is another equation. If we somehow write it down, I mean, we use a dimensionless number x, but we make a conversion and we find something. So basically, at the end of the day, this is how the behavior is going to look like. It's going to be some exponential of minus kappa squared or k squared x squared over 2. We want it to go like this, actually, for this case, because if you take the second derivative with respect to x of this expression, you will find that the difference between the second derivative and the x squared times the function itself is exactly this number, or with a minus in front of it. Okay, but for large x, this number is going to go to 0 anyway. It's going to be actually faster than the exponential because of that x squared. So this is actually good enough behavior, so we expect this one to be 0. Now the actual solution to the equation then, to the fundamental equation, will become then a combination of these two. So psi of x will be this function that we expect the behavior for it at infinity, times another function in here that we somehow have to make up so that the actual equation is satisfied. Okay, the h in here refers to Mr. Hermit, because if you do this one in here, you're going to find the equation that bears his name. So the equation you're going to end up with is Hermit equation, which is a mathematical equation to solve. Now what you want from this h of x is the following. You want it to, because it's going to be polynomial function, we want it a polynomial function where at some point it terminates, so that the exponential takes over and kills whatever behavior outside of that region. Okay, that is the trick of finding the energy in this case. That is how we find the energy is quantized. If we do this calculation, we find the energy for harmonic oscillator. We're going to define omega naught for harmonic oscillator square k over m, where k is that exact number that I wrote in there. I mean, I have so many k's in here, it's not even funny. So this is the k, but this is another k, so I'm going to write it as k prime, okay? Usually this is actually written as k prime for the properties of the harmonic oscillator. So this is k prime at this point in here to distinguish it from the wave number, okay? Because we have another k in this expression, so this potential has a k prime in it. So omega now is related actually to k prime, not to the wave number, to the restoring force, basically parameter for the potential that you have in there. So this is the classical omega that you guys did in physics 1, basically. Okay, so if I define omega naught that way, then the energy in this case is going to be quantized in such a way that it is equal to n plus 1/2 times h bar omega naught. Okay, this is the key thing that you remember for harmonic oscillator. The derivation for it is a little bit long and tedious, and it involves this Hermit polynomials, and it's really a fun derivation for math, but you really need to make sure to include the boundary conditions. This is kind of a boundary conditions. You don't want your electron to venture too much from this region, okay, even in their high energies in there, and you will find that the harmonic oscillator is a very good description of your solution. But this is basically in a nutshell, if you're doing the homework problems, this is what you will remember for the harmonic oscillator as the energy is quantized. Well, this omega naught is your classical angular velocity of a normal harmonic oscillator, which is the square root of the spring constant, divided by m. So the k prime in here is your spring constant in that model. Hooke's law, okay? So that's exactly what it is. So just to write it, to distinguish it from the k that we've been dealing with so far everywhere, which is the wave number, okay? This is in a nutshell the chapter, okay, for you guys. I think we covered all the materials. Please wait for another recording for solving some problems for this chapter. And then the next chapter, which is chapter 41, will deal mainly with the same equation, basically Schrodinger's equation, but in actually more than 1D, and we try to tackle the hydrogen atom and try to understand basically how molecules basically are formed, how the atoms basically are structured, how the molecules are formed, and how solids are formed. So we're really getting into fun stuff when it comes to these applications in here. Okay. If you guys have any questions, please let me know, and hopefully you're doing the reading in here and you're answering all of these things in here, part of the discussions in here that you're supposed to have for this class. Again, for the second part where we do the problems, you're supposed to do the problems. I want you really guys to understand all of the steps in here, and the fact that of how we derived. It's not really as important as how we derived actually Schrodinger's equation as much as how it is useful. Okay, but I gave you the reasoning of Mr. Schrodinger and how he came up with the equation that now bears his name, and I want you to really focus and ponder on what the meaning of this equation is. That's part of the discussion today. How this equation basically is. This is the full-fledged equation, yes, with x and t and all of that, and the fact that this is actually represents the entire energy of the system. This is the kinetic energy of the system, and this is the potential energy of the system. This is a natural extension of what we derived when it came to the free particles. So this is a particle in a potential, it doesn't matter what kind, well or no well, harmonic oscillator or no harmonic oscillator basically. So it doesn't matter which one you have, and this is the equation most of the time that we're going to deal. So we're going to write the equation and explain each and every one of those terms as part of this discussion, because you need to be familiar with it, the details of the solution. Also, it's very important that you have an explanation for what does it mean, because we came up with a complex number and we needed to understand what that complex number does for us. Thank you.